Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing Linear Algebra 1. This is Chapter 3, Geometric Vectors, Lines, and Planes. In Section 3.3, we're going to do the basis of a line, a plane, and space. 1 dimension, 2 dimensions, 3 dimensions, essentially, and then we can extend from there. That'll be the next chapter. This lecture, what we're going to do is a basis for n-dimensional spaces, in particular for when n equals 1 and 2. We'll do space after. We'll do 1 and 2 first. And then what we're going to do is get coordinates of geometric vectors in a given basis. All right, so we'll start with a line of vectors and what we call the real number, the set of all real numbers. We're trying to create a one-to-one correspondence between the line of vectors and the real numbers. Let u be an arbitrary non-zero vector, then the set of all vectors collinear to u is called that line of vectors spanned by u. And then we have a theorem I mentioned in the last video, but specifically now, if I have a non-zero vector u, any vector v which is collinear with u is a multiple of u, i.e. we have a unique non-zero alpha real number such that v is alpha u. We're going to use this idea specifically to create a basis for a line of vectors. What is a basis? We're going to do this dimension-wise, and then when we do it in the next chapter, a basis will be in general just something that has two properties. We'll go over that later. Right now, a basis for one dimension is what we call a basis for a line of vectors is any non-zero vector u in that line, i.e. it's on the line or parallel to that line. Moreover, if v is alpha u, we call alpha the coordinate of the vector v with respect to the basis. So what we're doing is, I'll do an example right away, but what we're doing is we're picking a line of vectors spanned by some vector u, but any non-zero vector could be a basis in there. And so when we pick a different basis, there's not one basis for a line of vectors. There's going to be infinitely many bases. Any non-zero vector in there can be a basis. Once we fix it, though, arbitrarily, you pick any one of those non-zero vectors to be the basis, then you can describe every other vector as multiples of that single vector, and then that's how we're going to get a one-dimensional coordinate from the basis of a line of vectors. Let's do an example. All right, example 1, what we're going to do is we have a grid here. We got 3 vectors in there. Vectors u, v, and w are all collinear. They're all going the same direction, even if some of them are oppositely directed to others. They all span, therefore, this same line of vectors, is what we're going to call it. This direction, or the horizontal from your perspective, is any vector in that direction is a basis for that line of vectors. In particular, the 3 that I drew, u, v, and w, are all bases for that line of vectors. Why? Because a basis is any single vector which is collinear to that line is going to be, or in the direction of that line, will be a basis for that line. Then because there's infinitely many over here, I pick 3 of them and any one of them can be a basis. I'm going to fix one of them. I'm going to choose u to be arbitrarily to be the basis of this line of vectors. Once I fix that and I call u the basis, with respect to this basis u, we have that v is, well, I look at u and u is 2 unit squares. So if that's the unit length now, u creates the unit length. So 2 squares is what we call 1. And therefore, what is v? V is 2, 4, 6. So it's 3 multiples of u. And it's in the same direction because the arrow is pointing in the same direction. So it's a positive 3 times u. And that's where we get the coordinates. This notation is overkill right now, but when we do 2 dimensions and 3 dimensions and then 15 dimensions or n dimensions, this notation will become, they're going to get more and more coordinates. How do you get coordinates? From the multiples in the description of this vector v with respect to the basis u. Therefore, 3 is the multiple in that relationship because they're collinear. Therefore, the coordinate of v with respect to the basis u is 3. Same thing with w now. W is pointed oppositely, and it is 3 units length long, and u is 2, so that means that w is negative 1.5 multiples of u. And that gives w the coordinate with respect to the basis u as negative 1.5. Right, the existence of a basis for a line of vectors allows us to turn any arbitrary line into what we're going to call a coordinate axis. How do we do that? We're going to pick an arbitrary point on L. We're going to call that the origin. Then we're going to translate u to that point. Wherever the terminal point of u ends on line L is going to be what we call a unit length. Once we have that unit length, we're going to try and describe coordinates of all other points on the line through this vector. How are we going to do that? Pick another arbitrary point A on this line L. Then we know from our theorem that A, we can create what we're going to call the position vector of A. How do we do that? Well, you just pick an arbitrary point A and you create the vector OA for every point on there. If you have another one B, Then you're going to create OB, and that'll create the position vector of B. So every point on this line now has an associated position vector. We also know that because they're all on the same line, therefore they're all collinear, our theorem tells us that OA, or this vector A, has to be a multiple of U. And that's what the coordinate of A is going to be, is this number alpha. And essentially what we've now done is, I'll erase and we'll recap this, but from this line scenario and taking an arbitrary vector and calling out the basis, what we're going to say is the coordinate of the point A is going to be this number alpha, which is the multiple of A with respect to our basis vector U. It's confusing, so let me rewrite that down and I'll recap in a second. Okay, to recap this, we have our line L, we have our origin, which is an arbitrary point on there, we have some vector which is non-zero in the direction of that line L, we move it over here so that we have our basis vector U arbitrarily. It creates a unit length, whatever the length of that vector is, we're just going to call 1 on the line now. Then we pick another point A on that line. I can create a position vector OA from that, which we're going to call A. Then what we have is the point A, or its position vector, corresponds to a unique number alpha. That number alpha is the multiple of U, which is equal to OA. What that does for us is, long story short, the coordinate of A is the same number alpha, which is the coordinate of the position vector OA with respect to the basis U. And what Mark really wants is we have a one-to-one correspondence between all position vectors, or all points on the line, and therefore the position vector. We have a one-to-one correspondence between all of those things and the set of all real numbers. What is that correspondence? For any point on that line or any position vector I can create from that, I have a unique number alpha. Why is it unique? The theorem tells us we have a unique number alpha, which is the multiple of U, because they're collinear. Conversely, for any number alpha that we have, I can create a position vector which is going to be just equal to alpha U. So if I have a point on there or a position vector, I can create a unique number alpha, which comes from writing it as a multiple of our basis vector U. And if I have an arbitrary number alpha, I can create a position vector with respect to that basis U, which will be alpha U. Therefore, we have what we call a one-to-one correspondence between the set of all real numbers and position vectors with respect to that basis U. Theorem: let U be a non-zero basis vector for a line of vectors, and let A and B be two positional vectors in this line. What if we want to add two vectors, or we want to scalar multiply two vectors, or linear operations? If we take the position vectors A and B and we want to add them, then what we're going to do is add their coordinates as well. In notation, if A has coordinate alpha with respect to the basis U, and B has coordinate beta with respect to the basis U, then A plus B is going to have the coordinate alpha plus beta. You're just going to be able to add the coordinates. Similarly, if I have a position vector which is going to be multiplied by a scalar, then what we're going to do is simply multiply its coordinate by the same scalar. So if A has coordinate alpha with respect to our basis U, Ka is just going to be the coordinate K times alpha. Let's prove that. All right, how do we see this? Proof of 1, what we're going to do is we're going to add A plus B. But we know something about A and B. This is hard at first, but we know that A has a coordinate representation with respect to our basis U. Everyone forgets the U because it's not there, but he's the ambient basis of everybody. He's describing everyone else. And B has a coordinate beta. What does that mean? A is a multiple of my basis vector U. And I know something about B. B is also a multiple of my basis vector U. And now I have U in both of these, so I can use my axioms of a vector space and say that I can factor this out. And this is going to be alpha plus beta times U. And that says if and only if the coordinate is going to be alpha plus beta, because this is the multiple in front of U on my basis vector. So A plus B has coordinate alpha plus beta. That's it. For the second one, if I'm going to do K times A, now you see where I'm going. This is where you steal. The key to ingenuity is hiding your sources. You steal the idea from me. From 1, what am I going to do? I turn A into its representation with respect to U and B. So I'm going to do the same thing. A, I know something about A. A is a multiple of U. And I'm going to associate the brackets, and that says that that will be K times alpha U, which means that its coordinate is K alpha. All right, to finish off a basis for a line of vectors, and then we'll move up one dimension to a plane of vectors. We have this result talking about the coordinate of, if we have 2 points on a line, what's the coordinate of the vector that joins A and B, not OA or OB. Those are the position vectors of the point A and B. But we're talking about specifically this vector now. What are the coordinates of that vector? So let A and B be 2 points on a coordinate axis. Again, our notation usually is marked like O, and if we're using basis, that's how we're going to describe a coordinate axis. We have an origin, which we fix arbitrarily, and we have a unit vector, which is non-zero, and then we place it there, and then that's how we describe, so that's the scenario every time. Once we have that, pick 2 points on there, then they're going to have respective coordinates alpha and beta with respect to this basis u. And what we want to know is, what is the coordinate of this vector AB? And everyone always wants it to be A minus B, but it is B minus A, or beta minus alpha. So why is that? The coordinate of the vector AB, this guy, is beta minus alpha, not alpha minus beta. And moreover, once we have that, the distance between A and B is going to be the absolute value of beta minus alpha. Proof. What we're going to do is, everyone forgets, but u is our basis. So what we have is we have a position vector OA, which is going to be some multiple of u, which says he has coordinate alpha. I remind you every time, that's how we get the coordinate alpha. And then we have some point B, and that position vector OB is some other multiple of u, and it gets a coordinate beta. Then what we're going to do with that is, I want to now know what this guy is. So AB is actually OB minus OA. How, yeah, that guy has to be this one subtracted off that one. And what is that now going to be? Once I have that clever idea, now I just use the same thing I did in the last theorem. OB has to be beta u, and OA is alpha u. And then I factor this out, and this will be beta minus alpha times u. So that position vector on here now, AB, is a beta minus alpha multiple of u, which says if and only if in our correspondence, beta minus alpha is the coordinate of AB. There we go. Then what are we going to do? We're going to use that idea again to take the norm of this vector now in the, I'll have to erase it for a second, but then we're going to take the norm of that vector and use the properties of norms, which I'll remind you as we go, and you'll see that we get absolute value. For 2, the distance between A and B, I erased our picture, but that is going to be the magnitude or the norm of the vector AB. And now we'll just use the same algebra that we used last time, just using norm now, and we'll have to remind ourselves of the properties of norm. What I now do is, what is that vector? We now know that that is actually beta minus alpha times u. We just went over that. Now, what I'm going to use is the property of this number. I don't know whether beta was larger than alpha or not, because these are real numbers. So when we have a multiple times a vector, and we're going to take its norm, I can take that an absolute value. So that will be beta minus alpha times the norm of just u. But the norm of u is 1 because it's a unit vector specifically. We've set his length specifically to be 1. So this is beta minus alpha times 1, which is the absolute value of beta minus alpha. So the distance between those 2 points is now the absolute value of beta minus alpha, which is the coordinate of the vector AB. Let's do 2 dimensions. Now what we're going to do is derive a plane of vectors and give a one-to-one correspondence between a plane of vectors and a copy of R2, or 2 space. Definition: 2 vectors are coplanar if they are in the same plane. Otherwise they're called non-coplanar. The set of all coplanar vectors is called a plane of vectors. What we're going to try and do is create a basis or a description of every vector in a plane of vectors, just like you described every vector in a line of vectors with respect to one basis vector. Now we're going to have 2 basis vectors, hopefully, if there's any justice in the world, and then we want to describe everybody in that plane of vectors with those and get coordinates for everybody in the plane. To do that, we notice that any 2 vectors can be brought into the same plane by placing their initial points together. And then this is actually a ramification of Euclidean geometry. One of the axioms says that there's exactly one plane containing 2 lines that intersect. So any 2 vectors are always coplanar. What we're going to do with that is theorem. If A is coplanar with 2 non-collinear vectors in that plane, same plane, then A is always a linear combination of u and v, i.e. A can be written as a multiple of u plus a multiple of v. And moreover, alpha and beta are unique. These coefficients are unique. What this says is if I have two non-collinear vectors, u and v, and if I have any other vector a which is coplanar with those two vectors, I can always describe uniquely a through these vectors u and v. And that's what we're going to want as what we're going to call a basis for a plane of vectors. Any two non-collinear vectors can be a basis for that plane of vectors. Let's give that definition. All right, as an example to illustrate this theorem, what the theorem is saying is if you have any two, so here's my u and here's my v. First of all, they're non-collinear. What does non-collinear mean? Collinear means that they're in the same direction. So this one's horizontal and this one is not horizontal. So they are definitely not in the same direction. So they are not collinear or non-collinear. Once I have that, all three of these vectors though are coplanar. What the theorem says is if I take two u and v which are non-collinear, not in the same direction in the same plane, any other vector a that I take in there, I must be able to describe as a linear combination, some multiple of u plus some multiple of v. And how do we see that? The best way to do that, instead of doing it in algebra and saying alpha, beta, and getting all of this stuff, let's just do an example and I'll show you, instead of proving the theorem, we'll just show you the idea of what we're going to construct. We're going to construct a parallelogram, and then we're going to use a definition of addition to create this linear combination. How do I do that? The longest story short, what we're going to do is I'm going to create right here this vector OM, and then I'm going to create this vector right here, which is, so I've created two more points, M and N. What I now have is two vectors, OM and ON. Once I create these two vectors, what I'm going to do is, now I see that OM as a vector, he's in this line of vectors. So using the previous as U is a basis vector for this line of vectors. Now I pick another point M on that line of vectors, and he must be a multiple of U. What is it? That says that this position vector is going to be 2U. Similarly, this is a line of vectors. V is a basis for that line of vectors because it's in the direction of that. Therefore, any point I notch off on that line of vectors, say N, has to be describe that position vector. ON must be a multiple of V. What is it specifically? ON is, V was 2 diagonal units, and this one seems to be 1, 2, 3 units. So this is going to be 3V. So first of all, and why have I done that? Because now I have a parallelogram which contains, as this guy is a diagonal, and then I can use the definition of addition to create A being a linear combination of U and V. Notice that if I translate this vector, he has the same direction as this vector and they have the same magnitude, so this is also OM, and this is now the vector ON. And so what does that say? That actually says that A, by definition, is this vector plus this vector. So this A is ON plus OM, which you'll see in a second. I'm going to turn around. This is OM plus ON, which is, what was ON? It was 2 multiples of U, and ON was 3 multiples of V. So that says clearly A is a linear combination of U and V, and I find the coordinates by doing this construction. You prove the theorem the same way. You pick an arbitrary 2 non-collinear vectors and you say you have another vector, and you create this parallelogram law with all of our indices and our notation, and that's the idea of what's going on. Why did I turn these around? I could have left it as ON plus OM, and then it would have been, I could also write this as A equals, algebraically, I don't see anything wrong with this. But we're going to create a basis, and I'm about to give the definition of basis. It has to be an ordered pair. You can't switch it around, and you always have to write your linear combination of all the other vectors in the specific order. The order now matters because I want to get coordinates from these linear combinations. Also, what that clearly says is A is a combination of U and V, so A is in the span of U and V. Let's give the definition specifically of a basis. The definition for a basis of a plane of vectors now is any ordered pair. That's important. U has to be first now when we do the linear combinations. If it's listed UV, if it's listed VU arbitrarily, then V has to be first in the linear combination. That's what we mean by ordered pair. The order matters. then any basis for a plane of vectors is any ordered pair u and v of specifically non-collinear vectors in that plane. And then if we have any other vector in that plane, we saw we can always describe, we have a theorem that says we can always describe any other vector as a linear combination of those two non-collinear vectors in the plane. If we can do that and we have that alpha 1 times u plus alpha 2 times v is that vector A, then the coordinates of that vector A with respect to the basis uv is going to be alpha 1, alpha 2. We're going to start writing it as a column vector. Basically what that says is, just like in one dimension, if you write a vector as a multiple of that single basis vector, then the coordinate is alpha. Now if you have two coordinates, we have to describe every vector in the plane of vectors as a linear combination of two vectors. Those coefficients in front of that linear combination become the coordinates of A with respect to the basis uv. Let's do one more result and then we're done with basis for lines and planes. And then we'll do 3-space next time. Just like we did for a line, now we have a plane. We get to add coordinate-wise essentially and scalar multiply onto each coordinate. Let u and v be an ordered basis of a plane of vectors, and let A have coordinates alpha 1, alpha 2 with respect to that basis uv, and let B have coordinates beta 1, beta 2 with respect to that. Again, what that means is A is alpha 1 u plus alpha 2 v, and B is beta 1 u plus beta 2 v. You get the coordinates from the linear combination of those basis vectors. What we're saying now is, what if you want to add A and B in that plane, or scalar multiply A in that plane? What that says is, when you add two vectors, you add their coordinates, specifically coordinate-wise. You're going to add the first coordinates and you're going to add the second coordinates, and that will be the coordinates of the addition of those two vectors. And when you scalar multiply, you scalar multiply each coordinate now by that same scalar k. Let's do one example. As a last example, we're going to want to give the coordinates of these vectors A and B with respect to the basis ij. First of all, why is ij a basis? Because they are non-collinear. In fact, they're what we're going to call perpendicular, and they're the canonical basis of 2-space. We'll get there eventually. Right now, all I need to know is I and j are not the same direction, so they are non-collinear, therefore they are a basis of the plane. I've given them as the listed ordered pair ij, so when I write the linear combinations of A and B, I have to list them as a multiple of I plus a multiple of j. I can't flip it because that will be the wrong coordinates. How do you get coordinates of one vector from two given vectors? You write this vector as a linear combination of those two vectors, and then the coefficients will be the coordinates of that vector with respect to the basis ij. What? Let's do that. First of all, I also did that specifically because nobody likes to do this, but you have to move the vector every time we do this. And the first one I did in the previous example, I already cooked up where the A was already in there. So if it's not, what I'm going to do is take the initial point of A and move it so it coincides with the initial point of these guys. Doing that, if I move him over, there's A now. And nobody likes that at first, but this is what we mean by when our two vectors equal. They're in the same direction and they have the same magnitude. Those vectors are both A. Now what am I going to do? Now I want to draw that parallelogram that we did in the previous example and write A as a linear combination of I and j. How am I going to get that? The easiest way is if I look at this vector, that is going to be negative I. And then if I create this vector, that is 1, 2 j's. And now from that picture, this vector plus this vector equals A. So what does that tell me? That says A is specifically now this vector, negative 1 times I, because negative I is negative 1 times I, plus 2 times j. And what does that tell me? That's if and only if the coordinates of A with respect to the basis ij is equal to negative 1, 2. It can't be 2, negative 1. This is what we mean by ordered pair. Similarly, for B, I have to move B. In this one, I'm just going to move it up one of the squares. There's B now. What do I have to do? I have to try and create some kind of triangle in there. Once I translated B up here, now I'm going to try and create this triangle again so I can use the definition of addition. This vector seems to be 2 i's this time. And then this one is going to be what specifically? Do you see what we've done here? This is negative j. That says that B is equal to 2 times I plus negative 1 times j. And that means the coordinates of the vector B with respect to the basis ij is equal to 2, -1. Those two vectors are clearly even in their geometric avatar. Hopefully they do not look equal to each other. And this is what we mean by creating the coordinates from an ordered pair, which we're going to call the basis. The order specifically matters. You can't just flip them. Please subscribe right here. I'll see you next time.